It's my pleasure to introduce Tengyu, who is from Ohio State currently, and he is a fourth-year PhD student doing his PhD with Yingbin Liang. And prior to USU, he earned his Bachelor of Engineers from Xi'an Jiaotong University, and he's interested in theory of reinforcement learning. Who would have thought that? He has written a bunch of interesting papers. Besides this, the finite sample analysis of SORSA with linear function approximation, stuff like that. Really interesting things. So besides RL, he's telling us that he's interested in AutoML and NLP, so really wide range of interests. And today he's going to talk about constraint policy optimization. Tengyu, the floor is yours.
Cool. Thank you, Chabas, for the kind introduction, and thank you all of you for coming to this talk. Today, I'm going to talk about our recent work, a primal approach to constraint policy optimization, global optimality and finite-time analysis. This is a joint work with my advisor, Professor Yingbin Liang from the Ohio State, and Professor Georgia Lan from the Georgia Tech. This is the outline of my presentation. So first, I'm going to briefly introduce the background of SafeRL and constraint MDP. Then I'm going to introduce our new proposed algorithm, CRPO. After that, I'm going to talk about the theoretical performance guarantee of our proposed algorithm, CRPO, which I'm going to focus on the main result and go through the proof sketch. Finally, I'm going to give a concluding remark and discuss about some possible future directions. First, about the SafeRL. So in the safe reinforcement learning problem, we not only want our agent to maximize the accumulated return, but also want our agent to ensuring the safe constraints. For example, in the autonomous driving, we want our car to follow a predefined route, and we also want our car to avoid obstacles and pedestrians, and also follow the traffic rule at the same time. Another example is the industry robot. In the assembly line, we want our robot to assemble a certain product, and we also want to make sure that the robot can avoid damaging itself or hurting the nearby people. So the problem in the safe reinforcement learning can usually be modeled as a constraint MDP. In this paper, we consider the infinite horizon setting with discounted reward and discounted cost. So basically, the constraint MDP is very similar to that of to the normal MDP, as both of them have state and action space, the transition kernel that are determined by the environment, and the initial state distribution, a discounting factor, and the reward. The only difference is that in addition to the reward, in the CMDP, we also define the cost function, which means that if an agent takes an action at a state, it not only receive a reward, but also will receive a cost. For example, in the autonomous driving task, if a car is getting closer to the target, then it may receive a reward +1. However, if the car also hit a pedestrian or run the red light at the same time, then it will receive a cost like -10 for punishment because it does not doing the right thing. So for each CMDP, we can define a policy, which is basically the probability of choosing an action at a condition on a given state, and based on the reward function, we can define the reward value function, which is basically the expectation of long-term accumulated reward conditional on the state or the state action pair and the policy. And we can also define the reward cost to go function, which is expectation of the long-term accumulated reward with respect conditional on the initial distribution and the policy. We can doing the similar things for the cost function. Yeah.
Oh, okay. So you're going to change in use reward and cost interchangeably. It's a little bit confusing. Or are we going to
But since they have a similar nature, so yeah, yeah, it's cost to go. It's just yeah. So
it will be cost?
no. It's like the objective function in the normal MDP.
So you want to maximize it or minimize it?
We want to maximize it. The reward is positive. And,
Okay.
Yeah.
Despite that, it's called C. That's fine.
The C0. Yeah.
Wanted to make sure.
Yeah. Cool. So for the cost function, we can do in the similar thing to define the cost value function and the cost to go function. Yeah, it's kind of confusing, but it has similar nature. And so the goal of the safe RL is to try to maximize the objective function, which is the reward cost to go function, and subject to a set of constraints, which just want to make sure that the cost to go function does not exist a certain threshold di. And in the safe RL, we defined the feasible set as a set of all the policy that satisfy all the constraints. And in generally speaking, such a feasible set could be a non-convex set. And we defined the optimal policy in the safe RL setting as the optimal policy that maximize the objective function within such a feasible set. To solve such a constraint problem, a standard and the most widely used approach is called the Primordial approach. So in the Primordial approach, we will construct an augmented Lagrangian function in which we augment the constraint function to the original objective function. And here, the lambda is called the Lagrangian multiply, which should be a non-negative number. So by doing that, after doing that, so instead of directly solving the constraint problem, which is almost untrackable due to since the feasible set is non-convex, now we can solve the following min-max problem instead, which is much more trackable. So, so in the Lagrangian,
Can I ask a quick question about when you say that the feasible set is non-convex, you mean the policy space or something like that?
Yeah, policy space, exactly.
Okay, because, well, if you would consider occupancy measures or something like that, this would be fine, right?
Yeah.
Okay.
So if we consider the function approximation setting and only consider the space of the parameter, and it, in generally speaking, it should also be a non-convex set. I will talk about the function approximation later.
Right. Yeah.
Cool. Yeah. So let's get continued. In the Lagrangian function, we usually call the parameter pi or the policy as the primal variable, and the Lagrangian multiply lambda as the dual variable. And in practice, we usually try to solve this min-max problem by alternatively update the primal variable and the dual variable. Specifically, the primal variable update is equivalent to an unconstrained policy optimization step with this hybrid reward, which is basically the negative reward plus the linear combination of the cost function. And the dual variable update is simply a projected gradient ascent. So in previous studies, a number of primordial approaches has been proposed and widely used in practice. And the convergence guarantee, or even the global convergence guarantee for the primordial approach has also been established. Another track of approach for the safe RL is called the primal approach. So in the primal approach, we do not need to introduce additional dual variable. And in the primal approach, the constraint is enforced by the designing of objective function or the updating process. Here are some examples of the primal approach. However, different from the primordial approach, so far, none of the above primal approach has been shown to have a global optimal convergence guarantee. So here I just summarize the comparison between the primal dual approach and the primal approach. So for the primal dual approach, it is very nice because we have a global convergence guarantee. However, people also find that this method is extremely sensitive to the hyperparameter, such as the initialization of the dual variable and the step size of both the dual variable and the primal variable. And this method is very popular and has been used for a very long time. However, for the primal approach is very easy to implement. I mean, compared with the primordial approach. So because we do not need to introduce additional dual variable, so we do not need to solve the very complex min-max problem. And however, so far, none of the primal approach has global convergence guarantee, and none of the existing primal approach has grounded evidence to actually outperform the primordial approach. And so far, the primal approach is not as popular as the primordial approach. So the primal approach has so many advantages. It is easy to use, and it also has achieved a great empirical success. A natural question to ask is, can we design a new primal approach that can outperform the primal dual approach in a principal way? If we can we also provide the global optimality guarantee for such a method? In our work, we address those two questions by proposing a new primal approach, which is called Constraint Rectified Policy Optimization, or CIPO. So before I introduce the design idea of our new algorithm, let's first take a close look at how the primal dual approach works. So recall that in the primal dual approach, we are trying to solve the following min-max problem, in which we try to minimize over the policy and maximize over the dual variable, which is a Lagrangian multiplier. And we will update or alternatively update between the primal variable and the dual variable to solve this min-max problem. So the primal dual approach basically try to enforce the satisfaction of constraints by the value of the dual variable, which is a Lagrangian multiplier. Specifically, if a constraint is violated, say the ith constraint, then we need the lambda I to be sufficiently large. In this way, the ith constraint can take a big weight in the Lagrangian function. So the policy optimization step can take a descending direction towards reducing the ith constraint function. On the other hand, if all the constraints are satisfied, in that case, we want all the lambda, all the dual variable lambda I to be 0, so that the policy optimization can fully work on maximizing the reward function. However, during the training, the lambda I or the dual variable can only be increased or reduced iteratively, which means that the value of lambda I cannot increase to a big number or reduce to 0 immediately. So it could cause a significant delay in response to the constraint violation or the constraint satisfaction. For example, if the constraint is violated, but the value of the lambda is very small, then the policy update will not be well aligned to reduce the constraint until the value of lambda is iteratively reduced to a very iteratively increased to be sufficiently large. So the reduction, in that case, the reduction of the constraint value will be delayed by those iterations that are used to increase the value of lambda. On the other hand, if the constraints are satisfied, but the value of lambda is very large, then the policy update will continue to reduce the constraint, even if we already in the feasible set, because the Lagrangian still contains a very large portion of the constraint value. until the lambda is iteratively reduced to 0. So this delay in the response could cause the overshoot of the constraint satisfaction, which is not unnecessary, and cause the reduction in the reward value improvement. So to summarize, the major drawback of the Primordial approach is that it has a delay in response to the constraint violation and the satisfaction. And in fact, due to such a reason, the empirical performance of a Primordial approach is very sensitive to the hyperparameter, such that the initialization of the dual variable and the step size of the dual variable. So typically, the successful implement of the Primordial approach requires extensive effort into the hyperparameter tuning, which is not desirable. So motivated by the drawback of the Primordial approach, our goal is to propose a new algorithm that can respond immediately to the constraint violation or the satisfaction. So inspired by this idea, here we propose our new algorithm, the CRPO. So our CRPO will alternatively update between the objective function and the constraint function. So specifically, if all the constraints are satisfied, then our algorithm will immediately switch to the objective function to work on the reward and to fully work on maximize the objective function. On the other hand, if there exists any constraint that are not satisfied, then our algorithm will immediately switch to the constraint function to fully work on the cost function to minimize the constraint value. So here I summarize the advantage of CRPO over the Primordial approach. So since our CRPO is based on the instantaneous evaluation of the constraints to switch between the constraint function and the objective function, so our algorithm can respond to the constraint more faster than the Primordial approach. And moreover, as I will show later, our CRPO can be implemented easily. Actually, CRPO can be implemented almost as easy as the unconstrained optimization method, because compared with the unconstrained policy optimization method, our CRPO only have one additional step. This step is we need to evaluate the constraint value before we update the policy. So besides that, it can be operated in almost the same way as the unconstrained policy optimization method. However, the Primordial approach needs to solve a very complex min-max problem, which is not easy to use in practice. The last is since our CRPO does not introduce any dual variable, so we won't suffer from the hyperparameter tuning issue, which is good. Then let's first take a look at the experiment. So in this experiment, we consider a very simple safe reinforcement learning problem in the Acrobot environment, in which the goal of the agent is to swing the end of the node link up to a given height. And the agent has 3 options in action: the positive talk, the negative talk, or just do nothing. And the agent will receive a reward when the second link, the end of the second link, is at a given height of 0.5. And in addition to that, we also will punish the agent if the agent apply the positive talk at the following 2 situations. So generally, basically, to summarize, we want the agent to reach a certain goal, but we will also punish the agent if the agent do something unwanted. So then let's look at the plot. In the plot, the green curve corresponds to the performance of unconstrained TRPO, and the red curve corresponds to the CRPO, and the blue curve corresponds to the Primordial approach. So from the plot, we can see that although the TRPO algorithm can achieve the highest reward, it cannot guarantee the satisfaction of the constraints. If we compare the performance of a CRPO and the primordial approach in terms of the return, we can find that our CRPO can achieve significantly higher reward within a given episodic than the primordial approach. So in terms of the constraint value, we can see that if both algorithms for CRPO and the primordial approach, if both algorithms start from an infeasible point, then our CRPO algorithm can move very fast towards the feasible set. However, the primordial approach is very slow. The reason is, as I have mentioned before, for our CRPO algorithm, when the constraint is violated, then the algorithm will fully work on the cost to reduce the constraint. However, the primordial approach heavily relies on the iteratively updated dual variable, so it could cause some delay. Moreover, even after those two algorithms enter into the feasible set, for our CRPO, well, after entering the feasible set, our CRPO is going to start to fully work on the reward to maximize the objective function. So you can see from the plot that the CRPO algorithm will stay at the boundary of the feasible set and actively explore the boundary to search for the global optimal and increase and keep improving the reward. However, yeah.
Yeah, I was just, you can finish, but I was wondering whether I missed it. Like, did we have like a pseudocoder or something? I have to admit that I was doing parallel stuff and I might have missed it, but a lot of other people also are asking the same question, like, what is exactly the algorithm doing?
You mean the algorithm?
Like, what is the algorithm exactly doing? Like this switching, how did it exactly work?
Yeah. So let me. Actually, I will show the whole the program, the algorithm later, but I can explain it briefly. Yeah. So
good. All right, that's what I wanted to know.
Yeah. So basically, if there exists first before we update the policy, we will need to check whether the constraint is satisfied or not. So if all the constraints are satisfied, then our algorithm will only maximize the objective function. It is the first case. In another case, if there exists any constraints that are not satisfied, then our algorithm will fully work on that constraint to reduce the constraint value. So that's the basic working principle of the algorithm. Yeah, okay. Then just continue. Cool. Yeah. So yeah, where I start? For the primordial approach. So even after the primordial approach enter into the feasible set, since the dual variable could still be very large, the primordial approach will continue to work on the constraint to further minimize the constraint value. So as we can see from the plot, the constraint value continued to decrease even after the line entering into the feasible region. So this overshoot in the constraint satisfaction could significantly hurt the performance in improving the reward. Yeah, that's the experiment. Then let me talk about the theoretical performance guarantee of the CRPO. First, let me go through the detail about the algorithm. So our first step is the policy evaluation. So before the update of the policy, we need to evaluate the Q function under the current policy. So by doing that, we can use, here we choose to use the temporal difference learning to do that. And actually, we can also use Monte Carlo, but here I just consider temporal difference learning. And the second step is the constraint estimation. So after we obtain the estimation of the Q function in the step 1, we can sample a mini batch of state action pairs from the initial distribution. And we can use the average of these state action pairs to construct an estimation of the constraint value. So also note that this step does not take additional sample complexity, because you can find that we only need a state action pairs. Yeah.
Finish.
Oh, okay. Yeah. Then yeah, let me finish first. Yeah, because well, we do not because we only need the state action pairs, and so this sample does not need to. We do not need to interact with the environment to sample those state and action pairs, and these samples can be completely generated virtually in the simulator. Yeah. So the question.
Yeah, quick clarification question. I noticed that you have 2 Q-bar function. One is indexed with pi t up there, pi t, and here in the bottom you have it indexed with t. They are the same?
Oh, they are the same. Sorry, it's a typo. I forgot.
No, it's just a small clarification question. Fine.
Yeah. Cool. Those are the same thing. Yeah. So then here comes the last step, the policy optimization. So in the policy optimization step, before we actually update the policy, we need to check the condition of the constraint. So how do we do that? So now in step 2, we have already estimated the value of the constraints. So we will make the judgment based on those estimations. First, in the first case, based on the constraint estimation, if there exists any constraint that are not satisfied up to a tolerance level, then we will use the policy optimization method to fully work on the constraint function to reduce the constraint value. In the case, if there exists multiple constraints that are violated, then we can randomly choose any one of them to minimize. In the second case, if all the constraints are satisfied, then we will completely ignore the constraint and fully work on the reward to increase the value of the objective function. So, and our CRPO can take a number of policy optimization methods, such as NPG, TRPO, and PPO. Yeah, then let's talk about the theory. So actually, in our original paper, we consider 2 cases, the turbulent case and the function approximation case. And since the analysis framework or in those 2 cases are basically very similar, in this talk, I'm going to focus on the function approximation case, which I think is more interesting. We consider using a neural network to parameterize both the value function and the policy. And for each state action pair, we will define a bounded feature vector for each state action pair, so that we can feed the information of state actions into the neural network. We consider a 2-layer neural network with parameter B and W, in which B indicates the weight of the output layer, and the W is the weight of the first layer. And we use ReNU as the activation pattern, activation function. And during the training, we will fix the weight of the parameter of the B and only update the parameter of the W. And we use this neural network to approximate the Q function. And we also consider a softmax policy in which the parameter tau represents the temperature parameter, and the function, the neural network function f, is the energy function. So here, let me talk about the first step, the result in the first step, policy evaluation. So let's just first recall the definition of a Q function. And since the Q function is well known that the Q function is a fixed point of the Bellman operator. So a standard way to evaluate the Q function is to use the TD learning, which basically moving our current estimation towards the bootstrap built on the current estimation. So, and here we consider the neural TD learning, which is basically the TD learning with neural network approximation with an additional step or additional projection step. So note that here we will require the TD learning to evaluate the Q function for both the reward and or the cost function. And in our algorithm here, we consider a nested loop setting, which means that each policy update is followed by a inner loop with capital K iterations of policy evaluation step. And we will use the average over those capital K steps as the final as the output for each for the policy evaluation, which I denote as theta bar Ki. So with this parameter, the neural network with this parameter is used as an estimator of the Q function. And the following theory establishes the estimation error bound in the policy evaluation part. So basically, under some mind regularity assumption, the neural tangent kernel assumption, and under appropriately step size, then we can upper bound the estimation error as two terms. The first term is the optimization error, which decreases as the number of iteration increases. And the second term is the function approximation error, which is caused by the insufficient expressed power of the neural network, which decreases as the number of neurons increases. Here the M is the number of neurons. And in fact, such a result has already been established in previous works, but in terms of in-expectation. Here we provide a high probability bound, which is slightly stronger than in-expectation. The reason we do that is, intuitively speaking, since the CRPO algorithm will switch between the objective between different functions, in order to establish the overall convergence for CRPO, here we need a stronger requirement convergence guarantee in the policy evaluation part. So that's the reason why we need to redo the analysis and provide a high probability bound. And the second step, the constraint estimation. This step is very simple. So as I have mentioned before, we will sample a mini batch of samples from the initial distribution and use the average and the Q estimation of Q function to formulate the estimation of the constraint value. So intuitively speaking, if our estimation of Q function, Q bar, is very accurate, and the samples are centered around the mean value, then the error of the estimation error of the constraint should also be very small. So here, in order to provide a high probability bound for the estimation, the constraint estimation error, we make a light tail assumption about the initial distribution for all the policy during the algorithm path. So this assumption can hold if we have a bounded state and action space. For our last part is the policy optimization. Here in our paper, we consider using the nature policy gradient as the optimizer. So I will briefly introduce the background of the NPG. So in the function approximation setting, the policy gradient has been derived by Schatten in this form. And for the nature policy gradient, the nature policy gradient can be viewed as the steepest ascent direction in the distributional space. And the updated direction of the NPG is the pseudo-inverse of the Fisher information multiply the full policy gradient. So to obtain the updated direction of the NPG, we have an alternative way. So let's consider this linear regression problem in which the target is the Q function and the base function is the score function. Yeah, I forgot to mention that. The phi represents the score function. So, and it can be checked easily that for this linear regression problem, the minimum solution of this problem is exactly the NPG update, meaning that if we can solve this linear regression if we can approximately solve this linear regression problem, then we can use this solution to approximately perform the NPG update. And in our paper, we also adopt this approach to do the NPG, to update the policy. The difference is that since in practice, we do not have the exact information of the Q function, so here we plug in the estimation of the Q function that we obtained in the first step of policy evaluation as the target, and try to solve this linear regression problem instead to obtain the direction delta t bar as to approximate the NPG update. Then let me introduce some notation and the definition. So note that in our algorithm, the parameter of the policy is controlled in terms of two parameters, the tau t, the temperature parameter, and the W, in which the parameter tau t controls the amplitude, and the Wt control the direction. So the multiply of tau t, Wt together serve as the actual parameter of our policy. And we also have a hyperparameter eta, which is the constrained violation tolerance level, which means that when we make the judgment, we allow the algorithm to make some very, very small mistakes in order to help them explore the boundary of the feasible set. So this is a hyperparameter, and as I will show later, our theory will naturally suggest a value for this tolerance level. The last is the set N0. So the set N0 is a set that connects all the feasible parameter over the algorithm path, and we will mention them again in the following algorithm. So let's now take a close look at how the policy update works in the CRPO. So before we update the policy, we will use the constraint estimation to check if all the constraints are satisfied up to the tolerance level. Then we think that the current policy is good and almost feasible. So we will add such a parameter into the set N0. After doing that, we will update the parameter by performing the NPG update to fully maximize the objective function. So note that the delta T0 represents the NPG update in terms of the reward. On the other hand, if there exists any constraint that are not satisfied, also up to the tolerance level, then we will pick any one of them who is being violated, and we will perform one step of NPG update to minimize the value of the constraint. Here the delta T IT represents is the NPG direction of the constraints. And then next I will talk about the convergence guarantee of the CRPO. So here in order to establish the overall convergence, I will require the following hyperparameter setting. So here we recall that the capital K is the iteration number in the policy evaluation step. So here we require the K increases as the number of neurons increases in order to guarantee the accuracy in the policy evaluation step. And for the tolerance level, we require the tolerance level to decrease in this manner, so that the violation cost is guaranteed to reach any accuracy level as long as the number of iteration T and the number of neurons increases. Note that the T is the iteration of the policy update and the K is the iteration of the policy evaluation update. We also require the learning rate for the NPG update as 1 over square root T, which decreases as the number of iteration increases. And the most important is that here we only choose the output of the algorithm uniformly from set N0. Recall that N0 is the set that connects all the almost feasible policy during the algorithm pass. And in the set N0, we only update the objective function. So our next theory establishes the convergence rate guarantee for our CRPO in terms of the optimality gap and the constraint violation cost. And we can find that the upper bound of those two irritants, both upper bound of those two irritants composes of two terms, in which the first term is the optimization error, and the second term is the function approximation error. And both of them achieve the rate of 1 over square root T if we ignore the function approximation error, and both error bound achieve the rate of 1 over square root T. Then let's compare the convergence guarantee convergence rate with the Primordial approach with some recent studies. So in terms of the optimality gap, in the function approximation setting, if we ignore the function approximation error, the CRPO can achieve the same convergence rate as a Primordial approach, which is 1 over square root T. However, in terms of the constraint violation, the CRPO is decays at a faster rate than the Primordial approach. So maybe it can demonstrate why the advantage of CRPO over the Primordial approach. Then let me briefly go through the proof sketch. So since we still have 5 minutes, I think, yeah. So let's go through that very quickly. So the first step is to establish the incremental progress of the NPG update in the function approximation setting. So from those two inequalities, we can find that the NPG update behave in a very similar way as the convex or concave optimization. And those two inequalities also tell us no matter under the NPG update, no matter if we maximize the objective function or minimize the constraint function, we can always, the algorithm is guaranteed to moving towards the reference point, which is a global optimal policy here. In the second step, we basically accumulate the incremental progress that we developed in the last step to obtain an optimality gap. So in the right-hand side of the inequality, it has 3 terms, in which the first term is an initialization error, the blue term is a variance error, and the green term is a function approximation error. So if we ignore the function approximation error, we can find that under the step size 1 over square root T, the summation of the initialization error and the variance error scales only at the rate of square root T, which means that if the cardinality of N0 is large enough, say the order of capital T, then we can guarantee a convergence rate of 1 over square root T for the optimality gap, meaning that if we can recall that in N0, we only update the objective function. So if we can, it means that if we can update the objective function with sufficiently many iterations, then the convergence of the optimality gap is guaranteed. In the next step, we provide we study some properties of the algorithm so that we can establish the overall convergence of the CIPO algorithm. So basically, under some appropriate hyperparameter setting, such as the iteration number of the policy evaluation, the mini batch that used to evaluate the constraints, and the tolerance level, then we have the following two conditions hold. Those two conditions are very important. So let's look at them. So the first condition says that the set N0 is non-empty. So it means that it guarantees that the output of our algorithm is non-trivial because we only select the output from the set N0. So for the second condition says that one of the following two statements must hold. So for the first statement, it says that the cardinality of N0 is scarce as capital T. So recall the last slide, as we have mentioned, if the cardinality of N0 scarce at capital T, then we can guarantee the convergence rate of guarantee the convergence rate of 1 over square root of T. And for the second case, if the second case, intuitively speaking, the second case basically says that the set N0 only contains almost global optimal point. So if the second condition holds, we can just divide both sides by the cardinality of N0, and then the convergence rate of 1 over square root T is trivially hold. So basically, this step, the two condition that we established in this step guarantee the convergence of 1 over square root T for the optimality gap. In our last step, we proceed to upper bound the constraint violation cost. So we find that the violation cost can be upper bounded by the tolerance level plus the approximation error of the constraints. And under appropriate hyperparameter setting, such as the iteration number of the policy evaluation and the mini batch size used to estimate the constraints, and we can make sure that the approximation error of the constraints is no larger than the tolerance level. So it basically says that the violation cost is totally controlled by the tolerance level. So as long as our tolerance level diminishes, we can also guarantee the violation cost of our output policy also diminishes. Yeah, that's the end of the proof sketch. So finally, let me give a quick concluding remark. So in this paper, we propose a novel primal approach called CIPO. It is easy to implement, almost as easy as unconstrained method. And we also demonstrated the advantage of CIPO over the primordial approach. And in theory, we established the global convergence rate for the CIPO. And for the future directions, it might be interesting to study in the case when we have a lot of constraints, whether can we enhance the scalability of our CIPO algorithms. And it is maybe also interesting to investigate if we use the instantaneous constraint rather than the accumulated cost. Well, how can we design a more efficient CIPO algorithm? So another direction is maybe we can, in the case when we have no exact information of the reward and the cost, can we still train the function? So can we still make the CIPO works? And the last interesting direction to study is, can we further improve the convergence rate of the CIPO if we use some tricks like the acceleration, smoothness, or add some regionalization? Yeah, that's the end of my talk. Thank you. Thanks. Yeah, any question?
Yes, thank you. I actually have a bunch of questions.
All right.
I think
yeah.
this is a very cool approach, and these are very nice results.
Yeah,
I
thanks.
do have questions about all the constants that you're hiding in those big O notations.
Yeah.
For example, it seems to me that this algorithm doesn't do like any conscious attempt at exploration, so there's no exploration bonuses. So I imagine that we're going to have some constants that are going to get pretty big, like some condition numbers of the feature matrices.
Yeah, exactly.
Can you tell us about those?
Yeah, cool. So actually, yeah, we can just go to the main theory because it's the most important part. So in the main theory, I actually had some the result does not show the result is actually depend on the conditional number such as 1 minus gamma. Yeah, it is a very important constant, but I do not show here. So yeah, for both error terms, we have 1 minus gamma here. Yeah, for the policy evaluation part, let me see. Yeah, we also have a theory for the policy evaluation. Yeah, for the policy evaluation, it also depends on the 1 minus gamma, and yeah, I did not show here. Yeah.
Right, but okay, so but I understand that you're using an NTK as well. So how do you expect that this condition number will be actually bounded? So I'm just wondering that, well, like besides this condition number, do you have like some other dependence on somehow?
Yeah. For example, yeah.
I don't know, like maximal information gain, or some kind of capacity of the NTK, some kind of complexity terms. No.
Yeah. For example, the number of neurons is an important parameter here. So I also have the it also has some dependence on the number of neurons in the optimization error term, because if the size of the neural network is so large, which means that the Lipschitz condition would also be very large, so it will in fact affect the optimization error. So yeah, the NTK will also have some constant contribution in the constant here.
I see. And I guess there's also some assumption that somehow your function is realizable with slow norm in the NTK, so like the smoothness of the true Q function.
Yeah.
I see. So there are many constants.
Yeah, there are many constants.
Really big here. I'm just wondering if you thought about sort of simplifying these results for the setting where you have like realizable linear function approximation.
Yeah.
So did you think about that setting, and how do you think that these results would look like in that case? What sort of quantities would your bound depend on in that case?
Yeah, that's a good question. In fact, we in our paper we also studied the turbulent case. So it's a very clean case. We do not have any. I don't have any assumption in that case. So in that case, I think the dependence so the convergence rate is also the same. It's 1 over. Let me go back to the convergence rate result. Yeah, it's here. So we still have we do not have function approximation errors anymore in turbulent case, and we only have the optimization error. So so in the turbulent case, we also have a convergence rate of square root t, 1 over square root t. Yeah, but we also depend on the cardinality of the state and action space. Of course, we have that. And we also have a dependent. I also show the dependence on the 1 minus gamma. I think, as I remember, it should be 1 minus gamma power 1.5. It's over here. So that's basically what the CRP works in a more clean setup.
Right, but I guess even in this setting, I'm afraid that you also have a factor of 1 over smallest probability. Right?
Yeah. It is typically required in the analysis of NPG. Yeah. We need to bound the. It seems like the important sampling fact because
Yeah, so this typically happens if you don't do any exploration. Then you pick up a factor of 1 over smallest probability, and this can be only avoided if you do something clever to explore, like upper confidence bands. But that seems to be compatible with the ideas in this algorithm. So to me, that sounds like the natural direction to extend these results in.
Yeah, sure. Yeah, because yes. So under the coverage assumption, the convergence proof could be more clean and easy to do. Yeah.
Yes. I think that this is still very nice. I'm just pointing out that, well, there is definitely room for improvement.
Yeah.
But that's for the experimental results and everything, and your justification against like primal dual approaches. I think this is a very nice story still.
Yeah.
Yes.
Thanks. And actually, the exploration is indeed a very interesting direction. I mean, it has already been done in the Primordial approach, I think, but it has not been done in the CRPO. Yeah, it's definitely a very interesting direction.
Right, and maybe like one more technical question that I have is, like, do you assume that Slater's condition also holds?
Slater's, no, I do not need Slater's conditions. I mean, yeah, Slater's conditions is typically required in the Primordial approach. So which means that we have zero duality gap. However, here I'm just totally primal approach. So I do not need any assumption about that. It is guaranteed to converge to the global.
Yes, that is also a very nice feature here. All right, thank you. So actually, there were like a bunch of questions in the chat during your talk. I don't know.
I have to check the chat.
Yeah, the chat was on fire all the time.
Oh.
So I don't know if there's any questions that are left unanswered there though. So Tin Duan had a bunch of questions. Maybe Tin, you want to unmute yourself and ask the most burning ones if you're still there.
Yeah.
Maybe he's gone. Tin.
Yeah.
He's probably a busy person. Too many meetings.
I do have a question.
Yeah.
Gabby, your hand's still up. That's a comment. Okay. Yeah. So you're comparing upper bounds when you're comparing with the primal dual method, right?
Yeah.
So is it possible that by, like maybe the analysis of the primal dual method is conservative on one hand, or it could be that there are some other ways of tuning it, right? Like primal dual is like a very big bag. And it strikes me a little bit as strange to find that the primal dual method is not competitive. At least I'm surprised. I understand your intuitive explanation, the way you explained it. I would think that if you have like a timescale separation between the primal and dual variables, dual variables would be on a fast timescale, the primal variables are on the slower, the normal timescale.
Yeah,
right?
exactly.
Then that problem that you described would basically go away.
Yeah, that's a good question. So in fact, let me just go back to the experiment. And actually, I have the same problem when I doing the experiment. So let me just show the plot. So yeah, so we can consider to solve the min-max problem in the 2-time scale method. Yeah, exactly. So actually the min-max problem in the let me go back to this. I think maybe better. Yeah, for this min-max problem, and we can check that it is for in terms of the dual variable, it is non-smooth convex. So it is although it is convex, but it is also non-smooth.
Right.
And for the dual variable, we can think that it is smooth, but it is a non-convex parameter. So we basically have
apart from the equivalent reparameterization that can happen with the occupancy state measures. So the non-convexity is kind of like a little bit of a red herring, I think, here.
Yeah. Also, we can also think of it as a convex. I mean, under the NP-J update, it is behaving like a convex organization. So it is fine if we consider as a convex.
Anyway.
So we basically consider a non-smooth convex and smooth concave min-max problem. So under such a problem, in order to establish the convergence guarantee for such a problem, the step size that in the slow time scale requires to be extremely small. So if I remember correctly, it should be epsilon power 6 or 8. I should be that level, but I cannot remember the exact. So
Karen's just writing in the chat, and that's how I remember as well. But I tried to find a paper which, in the tabular case, for the primal dual method, gets 1 over root t on both the main objective and the constraints. So basically the same speed. And yeah. And also, like, okay, maybe it's not smooth, but you can smooth it, and then we know that, like, okay, you can do this augmented Lagrangian stuff, and these things can help. So I was really wondering about, like, whether you really believe that the primal dual methods are not going to be competitive, or are you just saying that, like, in the current form, at the moment they're not competitive, and then maybe, like, you need to do something to them, or you need to do something to their analysis. So these are the different questions, right? So maybe we don't need to do anything to the algorithm, and the analysis would need to be improved. Although, like, I see that empirically they might be lagging, but I mean that's also, like, okay, like, empirical results are great, but they have their own limitations, right? And so the first question is, okay, do we need to change the algorithm? And then, okay, maybe we need to change the algorithm, but, like, is this really a dead end, or is it just like a small patch is needed?
So
this should have been the controversial part of the discussion. It's actually not that controversial. I don't think.
So Tengyu, maybe do you allow me to add some remarks?
Yeah, absolutely.
Yeah, sure. Yeah, first.
Yeah, so I agree with Jerba that, indeed, Primordial method has its advantages. For example, if you use this type of accelerated Primordial algorithm, smoothing all this, you can get even better convergence rate. You get 1 over k convergence rate, right, rather than 1 over square root of k.
Okay.
So so the advantage, the potential advantage of this primal approach is that it does not depend on the dual variables. So even though for accelerated primordial algorithm, you get 1 over k. Now let us think about the deterministic case. We don't have stochasticity. Everything is nice. Like you have convex, concave, and everything's nice. So you do gain something in terms of dependence on the number of iterations, but you do pay a price, because then the size of the dual variable will appear, and you don't have control of it. You don't know how big it is. If your Schneider condition is merely satisfied, then the size of the dual variable can be very big.
Or like the magnitude of the dual
Yeah,
variable.
the magnitude.
Oh, that's what you mean, right?
Yes,
okay.
But for the primal approach, we get rid of it. That's why, Tengyu, when he was performing some experiments, we will see, okay, if your feasibility will be violated, or in the open solution, or almost violated, then in that case, if I recall, correctly, Tengyu, please correct me. So in that case, the primal method will be the advantages of the primal method will be more apparent, right? In that case.
Yeah, sure.
And by the way, just curious, the augmentation techniques won't help with this leader's condition, or the near violation of this leader's condition?
Okay, sorry. Sorry, I didn't catch it because I got another phone call. So yeah.
Yeah. I was asking whether the augmented Lagrangian method, which is very popular for this.
Yes.
Wouldn't that be a remedy in this case when Slatter's condition?
I think even for all these methods, even for augmented Lagrangian method, because you need to perform dual updates. Whenever you need to perform dual updates, then it will depend on the size of the dual variables for sure, the magnitude of the dual variables. The other alternative, yeah, there are some other primal type methods, but this is one of the simplest ones, I think.
Perhaps I can add something. This is Yingbin from Ohio State University. So yeah, hi. I think it depends. So I think primal dual or primal depends from which perspective we look at it. For example, I think Tengyu mentioned a large number of constraints in the end. So if we have a large number of constraints, then I think in that case, primal dual may have an advantage in the sense that it actually addresses all these constraints together where they're dual variables. But in the primal approach, we kind of need to go from one constraint to another. That may time costly.
Yeah.
And so to improve the primal approach, there may be a way to improve it by linearly combine them together and handle them all at one time. But then those hyperparameters needs to adaptively tuned. So I think in that case, the primal dual may have an advantage. And on the other hand, so sometimes primal, it appears to us. So recently, George and I, so we had a new result as George mentioned. So we were able to improve the primal dual approach, improve the convergence rate by smooth the function, the dual function, so that you can apply the accelerated method to improve the rate to be 1/t. So in that sense, I think it seems to us it's sort of natural to do for primal dual, but we haven't figured out a way to design anything to improve the rate for primal yet, because the switch is actually done in a hard way, not in a soft way. So we haven't figured out a way to kind of smooth the algorithm so that we may be able to improve the rate.
Yeah.
Cool, thank you.
Yeah, so I had another question regarding this, like 1/√t versus 1/t rates. Is that, well, just imagine that you can do like perfect updates, right? Perfect Q functions and like perfect QI functions, and all these things are absolutely perfect. So then what rate would you be getting in the end? Because like NPG in the unconstrained setting gets like a 1/t rate in that case. Yeah. But here there was some discussion about this in the chat, but I really wonder what happens here. I do see that like switching between the primal and the dual, or like the constraints and the codes, can cause some problems. But can you explain?
Yeah, first, let me first talk about the CRPO algorithm. For our CRPO algorithm, it is very strange because CRPO algorithm intuitively it is a non-smooth optimization problem. So for the non-smooth optimization problem, no matter in the stochastic case or the deterministic case, we all have a convergence rate of 1/√t. Because the deterministic want help to improve the rate in the non-smooth case. However, as Professor Yingbin has mentioned, if we consider the primordial approach and if we smooth the primordial approach, then in the deterministic case, we can actually improve the rate of the primordial. And if we do not smooth the primordial approach, we can still obtain a convergence rate of 1/√t, because 1/√t is typically what we can expect in the non-smooth case. So, however, since not only the primordial approach can be smoothed, so only the primordial approach has the potential to be improved to the rate 1 over t by the smoothness technique. Yeah.
I see. No, I'm just asking because I actually believe that even without acceleration, it should be possible to get like a 1 over t rate, not with this algorithm, not with MPG, but rather with mirror descent working in the space of occupancy measures.
Oh, you mean mirror descent? Yeah. Yeah. So yeah, if maybe it's more detailed because things in the MPG update, the typical result for the deterministic MPG is 1 over t, right? Yeah, that's correct. So however, since now I need to switch between different objects, and such a switch will cause a non-smooth turn, which is a constant error bound. So in order to make sure that the constant error bound can diminish, I need to use a very small step size. As I showed here, I use a step size of 1 over square root t. Since the step size is very small, so I can only expect a convergence rate of 1 over square root t. However, in the unconstrained case for the MPG, the problem is actually smooth, so we can use a large constant step size for the MPG. Then, under the large constant step size, we can expect to obtain a better rate, for example, 1 over t. Yeah.
Right. Yes, I got it.
Yeah.
And then, like, still on the front of comparing guarantees with each other, because you say that, well, you get like 1 over root t, and other approaches also get like 1 over root t under certain conditions.
Yeah.
But here, t is the number of updates and not the number of samples that you're using, right? So, like, what would be the overall sample complexity of getting to, say, an epsilon optimal policy?
Epsilon, you mean for the CIPO?
Yeah.
Yeah, if we consider sample complexity is 1 over epsilon power 4, because we need to take the evaluation into consideration. So the total complexity is 1 over epsilon power 4. Yeah.
Right, but there exist primal dual approaches that get like 1 over epsilon squared, no? At least for the finite horizons, I think.
Okay, so
I think it's in the chat.
Oh, okay. Let me check the chat.
So you're saying for primal dual, in the stochastic sampling setting, there is a rate of 1 over epsilon square. Is that true?
Finite horizon case is
finite horizon. I guess there are regret bounds. If we change the regret bounds back to the
right, yes, that's what I mean. Like those regret bounds are like square root of t or t
so, okay.
So what was the question again?
Right, so I was just wondering about the sample complexity, and then as we discussed, well, apparently your sample complexity eventually is like 1 over epsilon to the 4, right?
Yeah.
And I was just wondering, like, is it really fair to compare these rates with other rates that are really given in terms of number of samples and not number of updates? And in particular, we were just discussing these results that imply 1 over epsilon squared sample complexity for learning a near optimal policy that satisfies the constraints.
Yeah, I don't remember exact algorithm. So was that just the sample complexity, or both the sample and computational complexity?
So the
in the regret setting, sometimes the computational complexity wasn't in the consideration, right? So here, I think, I agree. If just to compare the sample complexity, there might, it's possible. Yeah, the regret bound may suggest 1 over epsilon square. But here, actually, that sample complexity also represents the computational complexity.
Yes, I believe that this actually.
But I don't remember exactly the algorithm.
So yeah. So maybe I should ask Tengyu also to clarify. So in the convex setting, right? In the convex setting, the sampling complexity has two parts. One is to drive the algorithm. The other is to evaluate the constraint value.
Yeah.
So to drive the algorithm, like to move the iterates, the sampling complexity is 1 epsilon square.
Yeah. Iteration number, you mean, right?
Yeah, because each iteration just need one sample. So like the sample you need to run the algorithm, just like effective sample, I would say. But then the 1 epsilon to 4 comes from the fact that you need to evaluate the constraints. Because there you need to have 1 epsilon square to have to decide, you should move along the gradient or you should move along the objective or constraint.
Yeah.
So,
exactly.
but if I recall correctly, the evaluation of the constraint is a little cheaper, right? So you don't need to communicate with the environment or something like that.
Yeah, we can use offline or off-pause method because those samples could be fixed. We don't need to use U samples. Although in my paper I consider on-pause evaluation, but we can actually use offline samples. And in that case, our sample complexity will reduce to 1 over epsilon power 2.
But
yeah,
it's going to be really reduced because I saw that you need a higher accuracy there, maybe, to determine whether you're on the wrong side. And that is what's bringing up things. So even if you reuse the samples that were collected earlier, since you need a higher accuracy, I'm not sure, but like I see that like maybe that's why eventually you end up with 1 over epsilon to the 4.
Okay. Oh, yeah. So that's a good question. So as long as if the sample that we use to evaluation has good coverage, so definitely in that case we can use that. So it's a slightly stronger assumption, I think. If we do not have,
So well, my take on this, well, in case anybody cares, I guess my take on this is that, well, where this algorithm suffers is a sort of inefficient use of data, right? That in each optimization epoch, you just gather new data that you use for estimating the Q functions, and then you just calculate one update with this, and then you just move on, right?
Yeah.
And this is overcome by the competing algorithms with this idea of optimistic exploration, where you're not just estimating the current Q function, but rather an optimistic estimate of the Q function, like an upper confidence band on your reward Q function, and an upper confidence band on the constraint, or like the coast functions. And this way you can like reuse all the samples and still estimate the same object. I mean, I'm not sure if this idea is compatible with this algorithmic idea that you have.
Yeah.
But eventually it feels to me, well, since everything is trying to estimate the same object, right, the optimal Q function, you can reuse all the samples to build that estimator, whereas you cannot afford it here, or you cannot do it here.
I think it should be a very good idea to explore.
Yeah.
Yeah, maybe if one looks very carefully at what happens in a tabular case where everything is super clean.
Yeah.
Right.
Yeah.
And then you can have a better idea about how these things compare.
Right. So in the tabular case, you can just build a transition model, right?
Right.
Source all the data, and that would definitely improve your sample complexity.
Yeah.
You can do the same thing with linear MDPs.
Well, whether it's improvement or not, that's what we don't know, right? Like it is less than equal, but whether it's a improvement, that's the question. It could be.
Yeah, it could be more tighter. Yeah.
Very cool.
Yeah. Yes.
Yes, I agree. This is a very interesting approach.
Yeah. Thanks.
All right. So anybody else have any controversial questions? I don't know, Sharon, are all your questions answered?
Yeah.
One more.
Yeah, you go.
So in the convex setting, is this approach called something specific, like just doing descent on one of the constraints which are violated?
You mean if we apply the same method in the convex optimization?
Yeah. So like convex constraint optimization, what is the analog of this approach?
Yeah. Professor
I
Liang?
think George can answer it.
Okay, I can answer it. So, one of my earlier paper talk about this approach for convex optimization with expectation constraints. And even earlier in 1960s, Polyak, started this approach for deterministic problem. So what Tengyu has is something is even new in this paper is he was able to extend to multiple constraints. Before this approach is old, classical, but only deal with one constraint.
Oh,
yeah.
I see. All right. Okay. Thank you.
Oh, I like related question. Does it have a name? Did people give it a name?
Yeah.
Oh, sorry.
Like, did people give this approach to constraint optimization?
They don't give a name. I don't know a name. Okay, so my algorithm has a name in Convex. I call it cooperative stochastic approximation, and Polyak's cooperative stochastic approximation. I don't know if it's a good name, but
yeah, I like the name PPO.
Confusing, right?
Yeah, just trolling in the chat. All right.